Let's see, does the presentation come up?
Yes, it does. We can see it. We can hear you.
Awesome. Hi, everyone. My name is Giannina Guzman Caloca. I am a third-year graduate student at University of Maryland, College Park. I currently work with Eliza Kempton and will be starting a project with Drake Deming, but I also worked with Kevin Stevenson on Eureka, which is what I'm presenting today. Eureka is an end-to-end pipeline for JWST time series observations. I will be going through a little bit of so what can I tell you, right, about Eureka in just 10 minutes? So I'll just give a quick introduction to the code, talk about some basic functionalities of Eureka, just reference in literature, the fact that Eureka has already been used with data from JWST, and just talk about contributions and how the community can contribute to Eureka. And hopefully that gives kind of a good overview of the pipeline and a good overview of the code itself. So Eureka is, again, an end-to-end pipeline for JWST time series observations. It possesses the capabilities to reduce JWST time series data, just starting from the raw files and all the way down to extracting exoplanet transmission and emission spectra from these. We do have a JWST paper out, and the reference can be seen right there under Eureka. We have the code on GitHub, and we also have documentation with read the docs that you can look up. Eureka currently possesses the capabilities for JWST reduction methods for NIRCam time series imaging, NIRCam Grissom time series, NIRSpec, MIRI and LRS slitless spectroscopy, and it also supports spectroscopic HST WFC3 spatial scan observations. And I will be talking a little bit at the end of the fact that this is a working code, so it's heavily in development, and it's the reason why we would love for the community to help contribute to it, since it's open source. And the reason why we're doing this is because we want it to be openly available for the community and for early career scientists. So some of the basic functionalities and things that are necessary to know about Eureka, one of the big ones is ECF files. So ECF stands for Eureka Control File, and the file extension is like literally .ecf. These files are kind of a standardized file type, and they're used throughout all stages of Eureka to hold stage-specific parameters for direct control of the pipeline's behavior. So it makes it easier for the user to be able to control the pipeline's behavior without having to go into the source code and change things manually. Template ECF files are provided with the code on GitHub, and when you download the code during using the Eureka demos file or folder, the Eureka demos folder. So you'll be able to find template ECF files for this. There will also be, for stage 5, there is what's called an EPF file, Eureka parameter file, and it has the same, it basically is the same concept. It's a way for the user to control without having to go into the source code how the pipeline works. But in this EPF file is used to input planetary parameters in order to do the light curve fitting. So a little bit of an overview of the functionalities of each stage. Stage 1 and stage 2 are used for calibration of raw data. So converting ramps to slope and performing flap fielding, unit conversion. These 2 stages are optional because they actually are, in Eureka, they actually are a wrapper of the JWST pipeline. So these stages are not something that you have to go through, but if you want to go from end to end, it would be encouraged to use Eureka for them, but you don't have to, they're optional. Stage 3 performs background subtraction and spectral extraction. Stage 4 generates the light curves by binning the time series. Stage 5 is for fitting those light curves with noise and the astrophysical model. So that's why you need that EPF file so that you can input planetary parameters for the fitting. And stage 6, it displays the planet spectrum that you get from the data based on the outputs of stage 5. So basically, to kind of give a sense of, sorry about that, to kind of give a sense visually of how these stages and how the pipeline works. You can see from these graphics that you have a fits file, right, that comes in. So your raw data, and it depends on what stage you can start, right? So as I said, stage 1 and stage 2 are optional. They can be done with the JWST pipeline. And basically from there, you have your ECF files for the control of parameters that help with the pipeline. And then you have your stage 3, what goes into your stage 3, which can come from the JWST pipeline or just stage 1 and stage 2 from Eureka. Moving forward, stage 4 generates the light curves, as we talked about. Stage 5 takes as input, right, again, an ECF file, but also the EPF file that we talked about. And this is to do the light curve fitting that will eventually lead to stage 6, which gives us our final planetary spectra from starting from the raw data. So a little bit of in literature context. There are already 2 papers in review that have utilized Eureka in comparison with other pipelines. The reason why I have this here is just to show that Eureka performs well when compared to other pipelines. These are for WAPS 39b, and they're near spec prism observations. So just wanted to give context on the fact that Eureka is already being used for significant results in the community, which is really exciting. Installation and use, we do recommend the latest stable version. Again, this is a code that is heavily in development. You can play around with any version that you want, but if you really just for general use want to get a really good sense of how the pipeline works, we do recommend the latest stable version. And you can find out how to install it through the documentation. We have really detailed documentation for the code, and we even have a quick start guide in that section that you can use to kind of go through some examples and simulated data to see if the pipeline works for you. Finally, a little bit of how to contribute. One of the big things when it comes to contribution is like, do you have some sort of GitHub experience? Yes, right? Like I do. Well, awesome. That sounds like you understand how to fork repository, open issues, make pull requests. If you don't know how to do these things, that's completely fine. Our documentation actually has a contributing to Eureka section that includes details on how the testing works when you're contributing code, and also detailed documentation on how to use GitHub in order to contribute to open source software projects like Eureka. So hopefully that is a resource that is generally useful for the community. And finally, thank you. That is all that I have for y'all. I do want to say that we have put in a JWST archival cycle 2 proposal for software. This is a very community-based project, and a lot of this work couldn't have been done without this sort of community-based exchange of knowledge and work. So again, if this is something that is interesting to you and you want to jump in and you want to use it or you want to help contribute, the code is on GitHub, and we are open for contributions. So just read the documentation, figure out how to best contribute and how you can get in touch with the team, and make sure to check out the JWST paper if you want a little bit more context about the code. Aside from that, if you have any, I can take any questions, and yeah. Thank you.
Excellent. Thank you so much for this fantastic talk. I can, say that I really appreciate the accessibility of having documentation for both people that know how to use GitHub, and also don't know how to use. So great way to make science more accessible, more open source, by knocking down those barriers. Appreciate it. And we do have some time for questions right before the break. Does anyone have any questions? Please feel free to use the raise hand function to ask any questions. I'll also keep an eye on the chat if you'd rather just put it in the Slack channel or the chat.